Okay, so in the last video, we looked at one way to kind of approximate a solution to a differential equation when you couldn't solve it algebraically, using a slope field. And essentially, we graphed a whole lot of individual slopes through a bunch of points, and then we more or less connected the dots to get an idea of what our curves were. And then in theory, you would then be given an initial value to kind of show where you wanted to start your curve and kind of find the particular solution through that curve. So basically you start by graphing 100 different curves, and then you pick the one that you're told to find, the particular one you want. The alternative is to say, well, if I know that I have a differential equation, we'll just say y prime equals x minus y. And I know I have an initial condition. We'll just say I want to start at the point 1, 1. What if I wanted to find, let's see, the value of the function at x equals 3? So one thing we could do is draw a big slope field for this, find the initial condition 1, 1, sketch the curve, and then look at where the particular curve that we cared about, where that curve was when x was equal to 3, find the y value and approximate it that way. An alternative is to kind of do that on a smaller scale, meaning I could say, let's see, suppose I want to go through the point 1, 1. Well, I'm going to start here at 1, 1. And now I don't really know what the function is because I don't know how to solve that yet. But I do know at 1, 1, the slope is 1 minus 1, 0. And the slope is the rate of change, which means in theory, say if I wanted to find the value when x equals 3, this is 1, 1. So we'll just say that this is x equal to 3, we'll say right here, that's 2 and that's 3. I could say, well, if the slope is 0, then the value of the function should be 1 at 3. And that would at least be an approximation based on the slope. But then we understand, well, that's one way to do it, but if I want to make my approximation better, maybe I should approximate more. And this is where you get to have fun with your calculators again. So maybe I say, okay, if I want to know the value of the function at 3, I'm going to find what I think the value of the function at 2 is. Well, at 2, let's see, the slope was 1. The slope was 0 at 1. So at 2, I can assume the value of the function is 1. But now, use the slope of the function at 2 and see what I get. Let's see, if that's the point 2, 1, now y prime is equal to 2 minus 1, 1, which means from this point on, the slope should be 1. And I can use that to approximate my function. 3, let's see, if that's 2, 1, that's 3, 2. And essentially, I've used my understanding of the slope and broken that slope up into small increments and approximated the function value by kind of inching over using my idea of the slope. But now we understand how this is going to work. Well, if I got an approximation for the function by finding 2 sub-iterations right here, well, then how am I going to make the approximation better? I'm going to use 4. So maybe now I'll go over to 1.5. Then I'll find the slope at 1.5 and use that to approximate the value at 2. Then I'll find the slope at 2, use that to approximate the value at 2.5. Then approximate the slope at 2.5, use that to approximate the value at 3. And then that should help me approximate my function. And again, we understand how this works. Ultimately, the more iterations you do, the closer you'll get, but the more work you do. So ultimately, you kind of decide how much work do I want to do in order to get within the bounds that I care about, to have the least amount of error possible. Don't worry, for this, we're really not going to do error calculations, though, so we don't have to worry about that. But let's say, we'll work on this one right here. If we care about the name, this is called Euler's method. That's not Euler, that's Euler. Leonhard Euler, brilliant mathematician. But as far as this goes, there is a formula for this, and it's pretty straightforward, and it's in your book. But the way it works is, you start out with x sub 0, y sub 0, your initial point. Then x sub I plus 1 is equal to x sub I plus delta x. So you have an initial condition, in this case x sub 0, and then to find x sub 1, you use x sub 0 plus whatever your delta x is. I think for the one we're going to do that I just mentioned, we'll say a half. And you create a chart of values. You do the same for the y's. The y's look a little bit more complicated, but it's the same idea. Y sub I plus 1 is equal to your previous y value, plus, and now the way we're going to write this, f of x sub I, y sub I, delta x. And in this case, this f of x sub I, y sub I is just y prime. So basically, I'm just to make the notation work better, I'm going to say this differential equation y sub y prime is f of x sub I, because what do I do to find my new y value? I take the old one and I add the slope, which is this right here, times whatever my iterative value it is, a half, a fourth, whatever we go with. So for the purposes of this one, we're just going to say find x sub, I think we said we wanted to find x equal to 3. So we will go find x sub 4, y sub 4, if delta x is equal to a half. Because then if I start at 1, I'll get 1.5, 2, 2.5, 3. And that should be my fourth one. And I said I cared about the value at 3. So now it's just a matter of calculator button pushing, or in my case, working with a lot of fractions, and seeing what we get. The x's are easy. I have x sub 0, it's equal to 1. X sub 1 is equal to 1 plus a half by delta x, so that's 1.5. X sub 2 is equal to a half plus a half, which is 2. X sub 3 is equal to 2.5. And x sub 4 is equal to 3. Those are the easy ones. Now find the y's. So let's see. Y sub 0 is equal to 1. Y sub 1 is y sub 0 plus f of x sub 0, y sub 0, delta x. So for this, move this out of the way so I can have a nice clean table here. That becomes y sub 0, which is 1, plus this evaluated at the point 1, 1, which is 1 minus 1, 0, times a half, which gives me 1 plus 0, which is 1. Now I find y sub 2. Y sub 2 is y sub 1 plus f of x sub 1, y sub 1, delta x, which is y sub 1, 1, plus f of x sub 1, y sub 1. That's 1.5, 1. So x is 1.5. So I get 1.5 minus 1, which is a half, times delta x, which is a half. Half times a half is a fourth. That's 1 1/4, which is 5/4. And I'm going to use fractions here because I don't have a calculator readily available. Y sub 3 is y sub 2 plus f of x sub 2, y sub 2, delta x, which is y sub 2, 5/4, plus f of x sub 2, y sub 2. So that's 2 minus 5/4, which is 8/4 minus 5/4. That's 3/4 times a half. That's 3/8 plus 5/4, which is 3/8 plus 10/8, which is 13/8. And thankfully, this is the last time we have to do it. We get y sub 4 equals y sub 3 plus f of x sub 3, y sub 3, delta x. Y sub 3 was 13/8. plus f of x sub 3 y sub 3, which is going to be 2.5 minus 13/8. 2.5 in terms of eighths, that's 20/8 minus 13/8. That's 7/8 times a half. Good Lord, which is 13/8 plus 7/16, which is 26/16 plus 7/16, which is 33/16. Now I have my x sub 4, y sub 4. And it's equal to 33 over 16. And yes, if you're using your calculator, you can get the decimal for that, 2 1/16, which is not that hard, 2.0625. But again, as far as it goes, the formula, once you understand the formula, it's pretty straightforward and pretty simple. It's logical. It makes sense based on our understanding of functions and slopes. The process can be cumbersome, but again, it's somewhat cumbersome, more so for me because I don't have a calculator, so I have to do all the fractions, which is how they would have done it hundreds of years ago when Euler came up with this, because they didn't have calculators then. But if you're either going to throw it into Maple or you just have a calculator readily available, all these calculations are really straightforward. I would suggest, though, if you're using a calculator and you have decimals, which a lot of these would turn out to be, carry your solution to as many decimal places as you can until the very end here, because you want to be as accurate as possible. Fractions are exact, the decimals aren't. So if you have to round, carry to as many decimal places as possible. And again, ultimately, it's kind of a personal preference. You're given a differential equation, and you say, if I want to find the value at x equals 3, given this initial condition, I can create a slope field, sketch all the solution curves, and then find the curve that goes through 1, 1, and then see what it's doing at x equals 3 and approximate it that way. Or I can use Euler's method, where instead of finding all the general solutions and then picking the one I want, I start by picking the one I want, doing all the algebra out, and then approximating the solution that way. Personally, because you all know I don't like graphing things very much at all, because I don't think that way, I prefer this iterative algebraic way of doing it. The only problem is, again, if you're not a fan of doing all the algebra and all the math and calculations out, this can be really cumbersome. And again, we understand the question becomes, how accurate is that? Oh, well, I guess if we don't think it's accurate enough, maybe we make delta x equal to 1/4. And then I find x sub 8. Takes much longer, and that's kind of the trade-off. How exact do you want to be versus how much work do you actually have to do to get it? When is your approximation good enough? Ultimately, we don't know how to solve this just yet, but ultimately we'll know how to solve this, and then we can come back to it and see how close our answer is to the actual answer. But we'll save that for another day, because this video was long enough and I don't have enough time to do another one of these out. I will stress, though, right before I finish, you are going to need to do this. You can run it through Maple. That is completely fine. Both the slope fields and Euler's method, that is completely fine and time saving. Ultimately, on your exam, for both the slope fields and Euler's method, I want you to be able to write them out, which means you need to write all this out. You don't necessarily have to write this out. I did this because it's our first time seeing it and I want you to see the formula. But being able to write out y sub 1 is that, y sub 2 is that, y sub 3 is that. Even if you're just doing all this in your calculator, that's fine. But understand you're going to have to use Euler's method and approximate the solutions to these. And then again, once we know the other tricks, you'll be able to check yourself and see if your answer makes sense. We're just not there yet.